Hello, this is one of the lectures online video presentation moment about the last lecture, week number 6 of ele336 microprocessor architecture and programming. I'd like to give details about one of the most important user interface protocols or methods utilizing interrupts. Interrupts. There are many kinds of interrupts for our microprocessor. I will deal only with basic user interface type of interrupts. So let's begin. What's interrupts? Interrupts are special or specialized or specially defined subroutines. They are factory defined by hardware. Interrupts are actually small codes of programs run at certain instance requested by either software or hardware needs. So the codes are stored in specially designed addresses, and they are so-called factory defined. We do not write interrupt codes in this course. Rather, we will utilize them by calling or invoking them by int xxx, where x is a special hexadecimal interrupt code. The following codes are essential for our course. Actually, you can define up to 256 different interrupts. Some of them are defined for the microprocessor, but we will see only 5 of them and utilize in the examples or laboratory applications. Those are int33 hex, 10 hex, 14 hex, 16 hex, and 21 hex. Some of them by the examples in the classroom or self-examples by ele336, you have seen them. Let's begin with int33 hex. This is the code or interrupt routine has a code 33 hex. Why 33? There's no reason. It's just arbitrarily assigned by the first designers of the microprocessor long time ago. It's related to the mouse activities. So the mouse button clicks or other stuff by the user can be monitored by the software after invoking this interrupt. Detailed technical and software information about the interrupts can be found in Appendix D of your textbook. This Appendix D is also available as PDF file in star environments. One of the example is, okay, before invoking an interrupt call, okay, that int33 hex is basically an assembly code and its associated machine code, but you have to sometimes assign some registers for the interrupt before invoking it. For example, the most popular one is AX. Not all interrupts do have this specially dedicated registers or call registers, but some of them may. For example, if we assign AX06 hex value to X and invoke that interrupt, then the role of this interrupt is getting the button release information. For example, you see a mouse, left and right, and there can be a scroll lock, but beware that in the classical times of the microprocessor, not all the mouse functions were available. So we should be focusing on very basic mouse functions like left and right buttons, etc. There was no scroll wheel. Maybe MU8086 may utilize this special scroll wheel, but don't take a risk. Use the most simple ones. So there are two groups of information or register groups associated with the interrupt. One is called a group of registers needed or named as additional call register. The other group of register, result register. So you initialize, okay, that again may not apply to all interrupts. Not all the interrupts may have call registers, nor they may not have result register. Some interrupts may have both group of registers. So call register means the initializations to these registers should be made before the interrupt call, because the interrupt uses this number to arrange its background for requested task. Result registers means that this group of information in the memory presents what happens to registers after calling that interrupt. So AX06 is get button release information. The result of register of this interrupt call is BX register. Actually, 16 bits are used for very small pieces of information, left and right, 2 or 3 bits or so, but this also will be enough. So, button 0, that means the result register value 0 means left button is released. If it's 1, then right button. If both of them, the value of 2 is written to BX register, that means the center switch or button is released after invoking this interrupt. So we can check the user's behavior or input to the system by invoking that interrupt and recording the value of the BX register after it. So which button is released? After identifying which button is released, then the program may branch to related other tasks about this activity. Another result register is about this invoking. Your mouse cursor could be anywhere on the screen, and that screen, the cursor has coordinates, horizontal and vertical coordinates. In the old displays, the coordinate is a big box of so-called character box. Okay, so at that time, 40 columns and 25 rows were available to have 1000 character resolution screen. So the horizontal and vertical values of where the mouse cursor is stored in 2 registers. First, CX stores horizontal coordinate of this cursor, and DX stores the vertical coordinate. So as soon as you release the button information, that means you click something on the screen, and releasing means your cursor is over there, and you can test whether that coordinate belongs to a specified little box to do something related to the program. So that's one particular example for mouse activities, which is also much frequently used in the examples. Also, you may look up the Appendix D information about other possible interrupt call registers and result register for any specific activity related to the switches or buttons of the mice. The next interrupt 10 hex, is related to display. So it sets the mode of the display for the programmer. The call register, let's say popular call register again for this interrupt call is AX. Specifically, high byte of AX register is AH, sets the video mode. Currently, today's displays are mostly at worst VGA, and their resolutions are more than VGA, as you know. But in the prior times, when this microprocessor was first introduced into the market, there were several very low resolution color mode displays and their corresponding color graphics adapters. So AH stores the mode of these adapters, and AL also stores some other technical information. So, if you summarize, interrupt 10 hex is related to screen or monitor app operation. Before utilizing or invoking the call, you have to initialize video mode and related aspects to see the results of your program on the screen. So, in your examples, before the main program, you may see before the main program displays the results of any calculation or operation, it's absolutely necessary to set the video mode for correct display or presentation. So all the attributes, colors, resolution, other related parameters are set. From your appendix sheet, table D2 shows a list of video modes and definitions, like this format of 9 columns and some rows, okay? So for any information related to any value stored in lower byte of A registers, for example, particularly that 0 hex value on the left side, that corresponds to 320 by 200 pixels, and the whole screen is composed of 40 by 25 characters, and each character has a box of 8 by 8. That means 8 by 8 or 64 bits represents the, let's say, dotted version of the character. And it's either text or graph, so it's in the text mode or graph, etc. So this is the main information about the parameters related to the video displays. So the most suitable for our needs for this time is the best resolution in the previous era. AL, register AL, stores 13 hex. Pixel resolution is 320 by 200, and character box or character box resolution is 40 times 25, and each character is composed in 8 by 8 boxes, and it's a graphical mode. So not only text, but you can also have lines or graphical things, and others can be displayed on the screen. For example, set cursor position as an example. You set a page number related to video display and row and column values in byte contents of the DX register. And they should be, by setting this cursor position, there is no result operation. So you initialize and set the cursor at that certain coordinate on the screen for user interface. For example, you can also draw graphical things like a simple square at the almost center of the display and follow the drawing of that object, simple graphical object, to the screen. This was an house-made program, and the code of the program is given. The main code before the initialization is as listed. So assigning the values, okay, we have 5 assembly line of commands and then an interrupt calling. Okay, the header commands are name and offset or org command. Then 4 move commands assigns values to call registers, and interrupt is invoked. Interrupt 10 hex. Then Okay, this is like an initialization of the square or the display where the square will be drawn as a black surface. Okay. So next, the video mode is presented by assigning two values to call registers and invoking the interrupt 10 hex by utilizing that information by AL13 hex. You can follow that. The second assembly code is move AL13 hex that assigns the VGA mode. Then the program starts. This is a kind of known number of loop, just drawing each side of square by putting tiny little points at each iteration, okay? So you can follow the loop named or labeled with B1, assigning some values to the registers at different coordinates. These coordinates are stored in CX and DX. The value of CX is varied for horizontal direction and DX varied for vertical direction. And the loop is repeated number of times that equals to the length of the side of the square. So at the bottom, you see blue statement says that this part draws a horizontal line consisting of 100 pixels from coordinates 100 to 50, 100 extraction, 50 negative y direction mathematically, but computer screen positive direction is towards bottom in the vertical direction. And this continues up to pixel at 200 with the same vertical coordinate value of 50. Loop B2 draws a vertical line towards what? And then draws the second side of the square with the 100 repeated loop of labeled B2 as shown here. It's exactly the same method used in B1, only some numerical parameters are changed according to the new coordinates and the direction of drawing the line. The third loop, B3, draws the third line or segment of the square towards the bottom, similarly labeled as B3. And as you see, the numbers you can follow by working on the assembly code signifies these corner or boundary numbers. And the last fourth side is drawn accordingly, and the program stops at the beginning point of 100 horizontal direction and 50 vertical. So if you run the program, write the codes as shown. If you run the program step by step or full, okay, if you run the program continuously, this is a rather slow program. You can see the dot printing of the square easily by eye, okay? So it looks like this. So the square has green boundaries. You can also change the color of the dots. If you change the pixel color, then you change the color of the square drawn. So this is the emulator screen at the end of the program. And this is the result of the program after a DOSBox emulation. DOSBox emulation has very little graphical user interface options. So it just creates the COM file, and COM file is run at the terminal window under C command window, and then it shows the result directly, and this is a very quick run. So you just it's much faster than emulator. So I definitely suggest you run and see the results. And you may also develop your own programs by rectangles. Even you can also draw circles, which is a little bit complex because you have to utilize some trigonometric values for that. Okay, so I definitely suggest to play with these kind of graphical user interface or graphical display outputs. So next, interrupts. So we have covered mouse and display interrupts. The next interrupt, actually, we will not utilize it in our semester studies, but in the industry, still that old classical standard of serial communication exists. This is called RS-232 standard. And INT14 hex is related to the computer port release or access of this action or serial communication. So you may be utilizing this maybe later in some industrial applications. Interrupt 16 hex is related to the keyboard. So this is the third user interface. The keyboard has many keys, letters, alphanumerical characters, function keys, shift, control, alt keys, etc., etc. So any key pressed, the code of the key in ASCII, etc., can be stored in a result register. So by using this interrupt, the programmer can access to the information of the user interaction with the computer through the keyboard. There are many examples in the MA8086 about keyboard access. So this is a very typical, let's say, very simple one basic example of two call registers of AH keyboard reading. After a key is pressed, the value of the code, or sorry, the value of the key press is stored in lower byte of AX register. You can follow from bit number 0 to 7, shows either right shift pressed or left shift pressed, etc. Then you can follow any action of the user's fingers on the computer. INT21 hex, again, you have seen in many parts of the termination moments of the programs. The programs are in MU8086, example programs in MU8086 are ended with this command. Why? Because it transfers to the control to the DOS terminal so that a message appears, and in order to avoid everything erased in a second before we can read them is avoided or prevented by this interrupt. So this interrupt waits for the user command or pressing any key in the DOS environment. So this is a kind of end of DOS function call. So we have to set AH register to 4CH typically. Of course, it has many alternatives, but we won't be utilizing them all in this semester. Anybody who's interested, you may look up to the appendix sheet. As an example, program assembly code 2 sample ASM uses that INT21 hex. From appendix D, you can also find another group of codes and parameters which could be used in various applications. For example, that application, you can see the program in assembly code in blue characters towards the left side and its associated flowchart at the right side. So you can follow everything in assembly code and flowchart notation easily. So this example was introduced in the third or fourth weeks. Now it's shown again to show its INT21 hex code, because at that time I told that the interrupts will be explained later. So this is the moment. That program does everything. Move AH2, move DL, character 0, test bit of BL, etc. Then stops at the end of the routine calling INT21 hex on the screen to write the associated bit to the screen accordingly. After completing 8 bits on the screen, then the screen does not disappear, waits for the moment to receive the user interaction. That's the aim of this example. Now we have more examples. Of course, those are not the only examples. There are many more examples in the MA86. These are some of the codes or the flowcharts of some of the example codes in the MA86. For example, flowchart of colors ASM. So this is a kind of writing many or a number of bits or characters with different colors. So this is a good practice to learn which color corresponds to which hexadecimal number. Before printing the character, it's an interrupt because it shows on the character on the screen. Its color should be set as an attribute. So you can follow the attribute. So it's a continuous loop. So every time the character changes, its color also changes. Next is an example of mouse assembly code. Well, actually, this is a let's say a little bit complicated program, and its flowchart. It's nice to look everything on one page, but you cannot read. Either you make a very, let's say, let's try. Yeah, if you zoom it, not quite well, you can read, but you can understand something and you can follow. So the interested people can follow. Second example, mouse to ASM is better, more readable. It's better, so you can follow that it programs or flowchart starts with start ellipse or oval. Then each block is a procedure or a command or an operation. Each block with 2 parallel lines at the left and right side are subroutines. So those are called. For example, this is an interrupt 10 hex. Okay, so interrupts are shown with rectangles with 2 parallel lines on the right and left sides. So this is the method. Well, thanks for joining me online to this lecture. So this is an opportunity to make up our week number 6 online. So wishing you health and good luck. See you in our next meeting, lecture meeting.